For this problem, you have an electric field determined by this equation, and we're going to find the momentum and position of a negatively charged particle after 5 seconds and after 10 seconds. Firstly, we have to determine the electric field at the initial position. Using the equation, we just multiply the y component of the position by 3, getting 18, the z component by -5, which equals -20, and square 2, which is 4. And when we multiply that by the particle's charge, -0.01 coulombs, we find that the force on that particle at that position to be -0.18, 0.2, and -0.04 newtons. And to make our lives easier, we'll just solve for the initial momentum now, which is just the mass, 0.05 kilograms, multiplied by the initial velocity, 212 meters per second. This gives us an initial momentum of 0.1, 0.05, and 0.1 kilograms times meters per second. Then, using the momentum principle, the change in momentum equals the net force times the change in time, which we can rewrite to be the final momentum equals the initial momentum plus the net force multiplied by the change in time. Now we can plug in our known variables into the equation, the initial momentum, the force on the particle, and our time interval of 5 seconds. Then we multiply the components of the force by 5, getting -0.91 and -0.2 kilograms meters per second. Then we add that to our initial momentum to obtain the momentum of the particle after 5 seconds, which was -0.8, 1.05, and -1 kilograms meters per second. Then we can use this to obtain the position of the particle after 5 seconds using the position update equation. The final position equals the initial position plus the momentum over the mass times the change in time. Again, we'll just plug in our known variables, the momentum we just found, the initial position, our known mass, and our time interval, 5 seconds. First, we'll take the momentum and divide it by 0.05 kilograms, getting -16, 21, -2 meters per second. Then we'll multiply that by 5 seconds, which will get -80, 105, and -10 meters. Then we'll add the initial position to that, and we'll get -78, 111, and -6 meters. Now for the second iteration, we're just going to do all the same things again. First, we have to find the electrical field, so we're just going to input the position that we just found into the equation, which will get us 333, 30, and 6,084 newtons per coulomb. Then we'll want to multiply it by the charge of the particle to get -3.33, -0.3, and -60.84. And then, just as we did before, we're going to use the momentum update equation, plug in all our known variables, the initial momentum, the net force, and the time interval, and then we'll take the force and multiply it by the time interval to get -16.65, -1.5, and -304.2 kilograms meters per second, and we'll add the initial momentum to that to get -17.45, -0.45, and -304.3 kilograms meters per second. So we reused the time interval of 5 seconds because we were going from 5 seconds to 10 seconds, which is a change in time of 5 seconds. Then, using the position update formula, we're going to input our known variables, the initial position, the momentum we just found, the mass of the particle, and the change in time, which is again going to be 5 seconds. So, taking the momentum, we divide it by 0.05 kilograms, which will get us -349, -9, -6,086 meters per second. Then we'll multiply that by 5 seconds to get -1,745, -45, and -30,430 meters. Then we'll add that to the initial position to get -1,823, 66, and -30,436 meters.